All this good stuff, it could have been captured for posterity. I'll start now.
Oh, I do.
I do this sometimes.
Oh, really?
It's 9 plus 12. Minus 21. And then 9 plus 15 is 24. He said he was giving us another example. But yeah. I did the work in the exam. I'm getting we got a factor.
Oh, fine.
I was like, oh, okay. Got team?
So how'd we do? What did we do on this? Okay, what did we do? First of all, now there's a tendency, and don't get in the habit in math of overgeneralizing, because a lot of times what math teachers do, and I'm guilty too, is we're practicing something and you get 99 problems that all are like that. So what you always want to do first is what? Say it again.
Plug it in. Show the exception.
Well, okay, but I mean, if when you're doing this problem as a student or as a mathematician, what do you want to try first? Plug it in. Yeah, direct evaluation, right? Okay, remember that in reality, most of the time, direct evaluation is going to work, right? It's a rarity that it doesn't. In this case, if we try direct evaluation, what do we get? 0 to 0. What's that mean? More work. Okay. And in this case, the more work, being as I've got a rational function, polynomial on top, polynomial on the bottom, what's the more work? Factor. Absolutely, factor. So if we factor the top, and by the way, this is, you know, I am not in my personal life the most organized person in the world. And so if I can do this, you guys can do this. As a mathematician, you gotta, even somebody like me, who's got a messy garage, still has to, you know, if you want to be a good mathematician, you gotta be fairly meticulous about how you write things down. Now, don't get lazy and drop the limit notation, because it's important. We have not yet evaluated the limit. We haven't got an answer yet. And so there's a tendency for people just to put an equal sign there when they're doing their work, and then write the factored polynomials. That's not what we got though. We are still in the process of evaluating the limits, so I have to have that limit notation out front, which reminds me, I'm not done. I still haven't done the evaluation. So what does the top polynomial factor into? X minus 7, x plus 3, the bottom polynomial. Okay, and I'm taking this limit as x approaches. Oh, it's a different. I bet I know. I bet it's like virus hunting or something. So now, algebraically, I can cancel the x plus 3's, right? And now I can take my limit. Once I've done some cancellation, I can try direct evaluation again. And if I do that, as x goes to -3, I'm getting -10 over -11, which equals positive 10/11, right? That's my answer. Okay, makes sense? Okay, to finish things up, let's take one different kind of problem here. See if you can tell me what you might want to do here. This is a tricky one. I'll be impressed if you get this exact, but I'll give you a shot at it.
I can't believe
Okay, what do you think?
Sure. Is that -2 outside the root?
It is, yes. Yep. So if I try direct evaluation, what do I get? 0 over 0, don't I? Yeah. I get square root of 4, which is 2, minus 2 is 0, over 3 minus 3, which is 0 on the bottom, right?
Oh.
Okay, so once again, more work. But how am I going to do the more work this time? Well, factoring is not convenient. You actually could make it work, but it's a real struggle to make it work. You have to really work at it to get it to pan out for you. There's a better technique. What do you think? Now, part of the problem here is coming from the fact that what makes this difficult to deal with in terms of canceling factors is that darn square root probably, right? Okay. So now the problem is if I were to square the function, I'm getting a really different looking function, aren't I? Now that's cheating in a much bigger way than we did before. Before, when we traded for a different function, all we really were doing is just filling in a single point. If we changed all infinite points by changing the whole shape of the curve, that's not going to go well for us, is it? I mean, that's going to give us a different, the ant's walking on a completely different topography now, and the limits are going to change, right? So I can't really do anything like that. I can't change the look of the function that dramatically. I may still fill in that hole. But that's all we got here is a hole, by the way. Still just one of those cases where, because it's 0 over 0, so I've still just got an instance where this function would be, it is in math what we call well-behaved, except, really we do, except at that one point where we got that hole. What are some strategies in the past that you've used to deal with, maybe situations like this? I've got this factor on the top, square root of x plus 1, unfortunately, minus 2 that equals 0. Somehow I've got to algebraically try to manipulate the look of this thing so that I can.
Could you square? Square?
You already said we couldn't do that.
You can't do that. It's been suggested. Wait, question or suggestion?
Could you multiply it by x plus 3 on the top? That was cool.
I could, okay, well, now, here's what I maybe could do. This isn't necessarily going to be the answer. But if I wanted to multiply the top by x minus 3 for whatever reason, I would also have to multiply the bottom by x minus 3. And the reason being, if we go back to the identity properties for real numbers, we don't want to change the identity of this function, do we? With the possible exception of filling in that hole. The ant still has to be walking on the same kind of mountain range though, doesn't he? Right? Because that's all we're trying to find is where does the ant think he's going to step on this mountain or this topography. What can I do arithmetically, meaning by multiplying or adding, and not change something? What's the only number I could add to something and preserve its identity?
0.
I could add 0, right? So 0 is the additive identity. So I could somehow, in an algebraic tricky way, add 0 to this and change the look. That doesn't happen very often, honestly. I'm going to show you a couple rare cases in calculus where we use that idea. But more often, we use the multiplicative identity. What's the number we could multiply by 1? And you've done that a million times. You do that all the time, in fact. Let me give you a quick example. We'll come back to this. Without really necessarily calling it that or even knowing what you were doing, done that all the time. Anytime you add up fractions. For example, if I want to add up 1/2 plus 3/5, how are you going to add those fractions up? How do you have to add fractions? Common denominator, okay? But the denominators aren't common right now, so what do you do to get a common denominator?
Make it.
I'm going to multiply the first fraction by what?
5.
By, say it again?
5.
5, not just 5. I'm multiplying the
5 over
5 over 5. Aha, but what is 5 over 5 equal to?
1.
1. So are you changing the value of the first function?
No.
No, you're not. All you're doing is you're changing the look of the first fraction, right? So if I've got 5 over 5, and the second one, obviously by 2 over 2, this fraction is going to become 5/10, same thing as 1/2. This one becomes 6/10, same value as 3/5, but now they go together, don't they? They got the same denominators. So you do this stuff all the time. You just multiply it by the multiplicative identity, 1, in a creative way. It just changed the look, but not the value, right? We got to do that again. And then, so it's a good idea. X minus 3 isn't really the one we want to worry about, though. X minus 3 is easy to deal with. It's this top one. But you got the right idea. Okay, being as we're running out of time, I'm just going to throw something at you here. Do you remember talking about conjugates? Ever? What a conjugate is? That's a word you might remember, but maybe you don't remember what it means. Okay, here's what a conjugate is. Conjugates are this: A plus B and A minus B. If I have two terms, if they're added in one case and subtracted in the other case, then taken as a group, those are called conjugates. It's a conjugate pair, okay? So what we're going to do here is we're going to multiply the top and the bottom, so we're multiplying by 1. But we're going to choose the conjugate of this rational expression on the top. Okay, this is what we call a rationalizing technique. We're going to somehow try to get rid of this square root. And here's how we do it. This is really tricky. So we'll multiply top and bottom by the square root of x plus 1 plus 2 over the same thing. Okay, and what does that do for us? Well, on the top, if we FOIL this out, watch what happens. Now, remember that when we multiply conjugates, the real benefit of multiplying conjugates is, and this always works, if I multiply a plus b times a minus b, and I FOIL it out, I get a squared minus ab plus ab, right? Minus, oops. Minus b squared. The cross terms, the o and the I in the FOIL, always cancel when we're multiplying conjugates, don't they? Right? And so really, when you're multiplying, you're FOILing conjugates, you're just FOILing, just FLing them, you're not FOILing them. And so I know that when I FOIL these out, that's like my A, and that's my B, and that's my A, and that's my B, right? I'm just going to get the first term squared minus the second term squared, and the cross terms will go away. Agreed? Always. Okay, that's pretty good. On the bottom, I get sort of a mess, but not as big a mess as you might think. Because even though this is an ugly term just like that was, does this one go to 0 when x equals 3? No, it doesn't, right? This one did though, okay? So on the bottom, I get my x minus 3 times the quantity square root of x plus 1 plus 2. Okay, and now if I evaluate this directly, and I'm running out of time, I just hate this, I run out of time. What happens? Well, what is the square root of x plus 1 squared? X plus 1, right? Now I forgot to write limit, didn't I? Okay. So I get x plus 1 minus 4 over all this stuff. Okay, what is all this stuff on the top? X plus 1 minus 4 is, look at that.
That's great.
Well, that's the factor that's causing this thing to go to 0 over 0, isn't it? See that? So if I just cancel that factor, top and bottom. So now I've got a 1 on the top. Now I can take my limit, can't I? I got rid of the offending factors, the ones that were causing that indeterminacy. And now when x goes to 3, I just get 1 on the top. And on the bottom, I get the square root of 3 plus 1 is 4, plus 2 is 5. How about that for timing? Oh my goodness.